Welcome back, everybody. This is Keith Wiggins with PAG Waste Management. We're talking about the Handbook of Biomass Downdraft Gasifier Engine Systems, and we're on Chapter 5. And so let's get right into it. Here's the introduction to gasifier designs. Many different designs of gasifiers have been built and are described in the extensive literature on this subject. Bunch of references. Much of this material has been collected by A. Kopp of the University of California at Davis. Copies of these papers are also at SERI and German Appropriate Technology Exchange in Escoborn, West Germany. Anybody interested in design modification and improvement would be well advised to become acquainted with this material before repeating tried and tested techniques. However, many of the documented designs' variations are minor. We believe that future improvements to gasifiers will be based on a better understanding of the basic processes combined with improved measures of gasifier behavior and better regulation of fuel properties. Work is underway at various private and public centers to increase our understanding of the gasification process. Consequently, gasifier design is a state of flux. This makes it difficult to organize a handbook of gasifier design without having it out of date before the ink is dry. To avoid this problem, we will first describe the construction and operation of a number of historic gasifiers described in the literature to aid in understanding various trade-offs still under development. The reader must remember that the choice of gasifier is dictated by both the fuels that will be used and the use to which the gas will be put. We will then describe some gasifiers currently under development. Back in the 80s, you know. All right, so basic gasifier types. Fixed bed, sometimes called moving bed gasifiers, use a bed of solid fuel particles through which air and gas either pass up or down. They are the simplest type of gasifiers and the only ones suitable for small-scale application. That's very interesting to know. The downdraft gasifier was developed to convert high volatile fuels, wood, biomass, to low tar gas and therefore has proven to be the most successful design for power generation. We concern ourselves primarily with several forms of downdraft gasifiers in this chapter. As you can see, here's the illustration. It's a good illustration, actually. The updraft gasifier is widely used for coal gasification and non-volatile fuels such as charcoal. However, the high rate of tar production, 5 to 20%, makes them impractical for high volatile fuels where a clean gas is required. The fluidized beds are favored by many designers for gasifiers producing more than 40 gigajoules and for gasifiers using smaller particle feedstock sizes. In a fluidized bed, air rises through a grate at high velocity, at a high enough velocity to levitate the particles above the grate, thus forming a fluidized bed. Above the bed itself, the vessel increases in diameter, lowering the gas velocity and causing the particles to recirculate within the bed itself. The recirculation results in high heat and mass transfer between particle and gas stream. Suspended particle gasifiers move a suspension of biomass particles through a hot furnace, causing pyrolysis, combustion, and reduction to give producer gas. Neither fluidized bed nor suspended particle gasifiers have been developed for small-scale engine use. We have already mentioned that gasifier designs will differ for different feedstocks, and special gasifiers have been developed to handle specific forms of biomass feedstocks, such as municipal solid wastes and rice hulls. The manner in which ash is removed determines whether the gasifier is classified as either a dry ash, ash is removed as powder, or slagging, ash is removed as molten slag gasifier. Slagging updraft gasifiers for biomass and coal have been operated at only a very large scale. Charcoal gasifiers. Updraft charcoal gasifiers were the first to be developed for vehicle operation. They are suitable only for low tar fuels such as charcoal and coke. That figure 5.4 right here shows an updraft charcoal gasifier that was used in the early part of World War II. Air enters the updraft gasifier from below the grate and flows upward through the bed to produce a combustible gas. High temperatures at the air inlet can easily cause slagging or destruction of the grate, and often some steam or CO2 is added to the inlet air to moderate the grate temperature. Charcoal updraft gasifiers are characterized by comparatively long starting times and poor response because of the large thermal mass of the hearth and fuel zone. Charcoal manufacture is relatively simple and is on in most countries. However, it requires tight controls on manufacturing conditions to produce a charcoal low in volatile content that is suitable for use in charcoal gasifiers. Charcoal versus biomass fuels. High grade charcoal is an attractive fuel for gasifiers because producer gas from charcoal, which contains very little tar and condensate, is the simplest gas to clean. Charcoal gasifiers were restricted over much of Europe during later years of World War II because charcoal manufacture wastes half of the energy in the wood. On the other hand, Australia worked. Aus- Australia worked almost exclusively with charcoal during this period because of that country's large forest acreage and small number of vehicles. Nevertheless, the simplicity of charcoal gasification has attracted many investigators, and more than 2,000 charcoal systems have been manufactured in the Philippines. A large number are not currently working. Uh, period. Okay, next section. Cross-draft gasifier. The cross-draft gasifier, shown in figure 5.5 right here, is the simplest and lightest gasifier. Air enters at high velocity through a single nozzle, induces substantial circulation, and flows across the bed of fuel and char. This produces very high temperatures in a very small volume and results in in production of low tar gas, permitting rapid adjustment to engine load changes. The fuel and ash served as insulation for the walls of the gasifier, permitting mild steel construction for all parts except the nozzles and grates, which may require refractory alloys or some cooling. Air-cooled or water-cooled nozzles are often required. The high temperatures reached require low ash fuel to prevent slagging. The cross-draft gasifier is generally considered suitable for only low-tar fuels. Some success has been observed with unpyrolized biomass, but the nozzle-to-grate spacing is critical. Unscreened fuels that do not feed into the gasifier freely are prone to bridging and channeling, and the collapse of the bridge fills the hearth zone with unpyrolized biomass, leading to momentarily high rates of tar production. The fuel size is also very important for proper operation. Cross-draft gasifiers have the fastest response time and the smallest thermal mass of any gas producers because there is a minimum inventory of hot charcoal. In one design, a downdraft gasifier could be operated in a cross-draft scheme during startup in order to minimize the startup time. Very interesting. 5.6. The updraft gasifier. The updraft gasifier has been the principal gasifier used for coal for 150 years, and there are dozens in operation around the world. In fact, World War II type Lurgi gasifiers now produce a large share of the gasoline used in South Africa by oxygen gasification, followed by the Fischer-Tropsch catalytic conversion of the gas to gasoline. The geometry of the updraft gasifier is shown in figures 4.5, 5.3, and 5.4. During operation, biomass is fed into the top while airstream are fed through a grate, which often is covered with ash. The grate is at the base of the gasifier, and the airstream reacts there with charcoal from the biomass to produce very hot CO2 and H2O. In turn, the CO2 and H2O react endothermically with the char to form carbon monoxide and hydrogen. The temperatures at the grate must be limited by adding either steam or recycled exhaust gas to prevent damage to the grate and slagging from the high temperatures generated when carbon reacts with the air. The ascending, hot, reducing gases pyrolyze all the incoming biomass and cool down until in the process. Usually, 5 to 20% of the tars and oils are produced at temperatures too low for significant cracking and are carried out in the gas stream. The remaining heat dries the incoming wet biomass so that almost none of the energy is lost as sensible heat in the gas. The updraft gasifier throughput is limited to about 10 gigajoules, either by bed stability or by incipient fluidization, slagging, and overheating. Large updraft gasifiers are sometimes operated in the slagging mode, in which all the ash is melted on the hearth. This is particularly useful for high ash fuels such as municipal solid waste. Both the Purox and Ancotorax processes operate in the slagging mode. Slagging updraft gasifiers have both a slow response time and a long startup period because of the large thermal mass involved. All right. Next, so we'll stop after this next section, the invert downdraft gasifier. Here's the intro. The nozzle and constricted hearth downdraft gasifiers, shown in figure 4.5, 5.4, and 5.5, is sometimes called the invert gasifier after its entrepreneurial inventor, Jacques Imbert, although it was produced by dozens of companies under other names during World War II. Approximately 1 million of these gasifiers were mass-produced during World War II at a cost of about $1,000 in 1983 US. I don't know if that's a million today or something. It is important to realize that the cost of producing such a unit today would depend primarily on the degree to which it could be mass-produced, since none of the components are inherently expensive. Air gasifiers can be operated either by forcing air through the fuel, pressurized by drawing the air through the fuel suction. In practice, gasifiers that fuel engines generally use the suction of the engine to move air through the gasifier and cleanup train, and these are called suction gasifiers. We will describe only suction gasifiers here. However, only minor modifications are required to build pressurized gasifiers. We go over that in Chapter 8, which deals with the topics of blowers, fans, ejectors, and compressors. A large number of descriptive articles on gasifiers appeared during World War II, but no detailed drawings have been located from that period. Fortunately, formulas for determining critical dimensions are given in a number of older references. Renewed interest in biomass gasification has manifested itself in the fact that a number of individuals and groups have built modern versions of the Imbert gasifier. Plans and manuals for constructing some of these designs are available from several groups, and it lists them. Some of these gasifiers have been attached to cars and trucks that have succeeded in traversing the country on several occasions. In particular, Mother Earth News and its subsidiary, Experimental Vehicle News, have performed extensive tests on gasifiers and have published informative articles and plans with photographs of fabrication steps. The plans are sufficiently detailed so that a skilled welder can fabricate a gasifier for relatively small expense. In 1978, a number of tests were performed under a SERI contract on a 75 horsepower Hesselmann Imbert type downdraft gasifier. This gasifier was built in Sweden at the end of World War II and was imported to this country by Professor Bally of the University of West Virginia. Professor Bally used the gasifier in tests during which the gasifier operated on wood pellets, and oxygen. Subsequently, the gasifier was sent to SERI in Colorado for further testing with a 15 kilowatt Onan electric generator. More recently, the gasifier has been used to gasify peat by Professor Goldhammer at Lowell University. The gasifier is now being used by syngas systems to generate producer gas to test gas cleanup systems for use with its 750 kilowatt power generator. Although much of the testing was qualitative in nature, the authors have considered considerable experience in running this interesting technological antique. So, description of the downdraft Imbert gasifier. Referring to those previous figures, the upper cylindrical part of the inner chamber is simply a magazine for the wood chips or other biomass fuel. During operation, this chamber is filled every few hours as required. The spring-loaded cover is opened to charge the gasifier, and then it is closed during gasifier operation. The spring permits the cover to pop open to relieve pressure in case of gas explosion, thus functioning as a safety valve. About 1/3 of the way up from the bottom, there is a set of radially directed air nozzles that permit air to be drawn into the chips as they move down to be gasified. Typically, there are an odd number of nozzles so that the hot gases from one nozzle do not impinge on the opposite nozzle. The nozzles are attached to a distribution manifold that in turn is attached to the outer surface of the inner can. This manifold is connected through the outer can to a large air entry port. One air nozzle is in line with this port, allowing the operator to ignite the charcoal bed through this nozzle. During operation, the incoming air burns and pyrolyzes some of the wood, most of the tars and oils, and some of the charcoal that fills the gasifier below the nozzles. Most of the mass of the biomass is converted to gas within this flaming combustion zone, since biomass contains more than 80% volatile matter. The gasifier is in many ways self-adjusting. If there is insufficient charcoal at the air nozzles, more wood is burned and pyrolyzed to make more charcoal. If too much char forms during the high load conditions, then the char level rises the nozzle so that the incoming air burns the char to reduce the char level. Thus, the reaction zone is maintained at the nozzles. Below the air nozzle zone lies the gas reduction zone, usually consisting of classical Imbert hearth, or in later years of the V hearth. Most recently, the flat plate hearth constriction has been introduced. The latter two hearth designs accumulate a layer of retained ash to form a high-quality, self-repairing insulation. Improved insulation in the hearth results in lower tar production and higher efficiency over a wider range of operating conditions. After the combustion pyrolysis of wood and hot charcoal at the nozzle level, the resulting hot combustion gases, CO2 and H2O, pass into this hot char, where they are partially reduced to fuel gases, carbon monoxide and hydrogen. This procedure results in marked cooling of the gas, as sensible gas heat is converted into chemical energy. This removes most of the charcoal and improves quality of the gas. Eventually, the charcoal is dissolved by one of these gases and disintegrates to smaller chunks and a fine powder that either is swept out of the gases to be cyclone separator or falls through the grate. Tars that have escaped combustion at the nozzle may crack further in hot char, allowing the tar cracking is now thought to occur only above 850 degrees Celsius. The spaces between the nozzles allow some unpyrolized biomass to pass through. The hearth construction then causes all gases to pass through the hot zone at the constriction, thus giving maximum mixing and minimum heat loss. The highest temperatures are reached in this section, so the hearth constriction should be replaceable. If terry gas is produced from this type of gasifier, common practice is to reduce the hearth constriction area until low tar gas is produced. However, one should remember that hearth dimensions also play a role in the gas production rate. The fine char ash dust can eventually clog the charcoal bed and will reduce the gas flow unless the dust is removed. The charcoal is supported by a movable grate and can be shaken at intervals. Ash builds up below the grate and can be removed during the cleaning operations. Usually, wood contains less than 1% ash. However, as the charcoal is consumed, it eventually collapses to form a powdered char ash that may represent 2 to 10% of the total biomass, in turn containing 10 to 50% ash. Ash contents depend on the char content of the wood and the degree of agitation. The greater the degree of the char reduction, the smaller the resulting particles and the higher the ash, as shown in Figure 3.3. The downdraft gasifier startup and response time is intermediate between the fast cross-draft gasifier and the slow updraft gasifier. The Imbert gasifier requires low moisture, less than 20% moisture, and uniformly blocky fuel in order to allow easy gravity feeding through the constricted hearth. Twigs, sticks, and bark shreds must be completely removed. The reduction in the area at the hearth and the protruding nozzles presents hazards at which the passage of the fuel can be restricted, thus causing bridging and channeling, followed by high tar output, as unpyrolized biomass falls into the reaction zone. The vehicle units of the World War II era had ample vibration to jar the carefully sized wood blocks through. In fact, an entire industry emerged for preparing char wood at that time. All right, let's stop right there. We'll pick it up at 5.7.3, superficial velocity, hearth load, and gasifier sizing. Thank you so much for listening. We'll talk to you next time.